Okay, so this is a recap from last class. Today we're going to talk about equilibrium, and we're going to start talking about the equilibrium constant. So just to recap, equilibrium is represented with a capital K and a little subscript EQ, which stands for equilibrium. And really what's important to remember that equilibrium is really a ratio of the forward and the reverse rate constants. So the capital K is a ratio of lowercase k divided by lowercase k of the forward and the reverse reactions. So for example, if we have nitrogen dioxide making N2O4, the forward reaction has a rate constant of lowercase k subscript f, and the reverse reaction has lowercase k subscript r for reverse. This tells us, the double-headed arrow tells us that the rate of the forward reaction is equal to the rate of the reverse reaction. So if we equate that, and we write again our rate law in terms of the starting materials, we equate the two together, and then we set up the equation so that we have Kf divided by Kr. This gives us N2O4 divided by NO2 squared, which equals K equilibrium. And the way we write equilibrium is that we write the products in the numerator and the reactants in the denominator. For a general reaction, if we have A plus B making C and D, the lowercase letters are the stoichiometric coefficients, the capitals are the actual concentrations. So K equilibrium, sometimes you will see it written as Kc, and C stands for concentration in this case. We have products, the product of the concentrations of D, C and D raised to the power of their stoichiometric coefficients divided by the product of the concentrations of the reactants raised to the power of their stoichiometric coefficients. If K equilibrium is large, if it is a very large number because it is a ratio, this tells us that the numerator is large, and if the numerator is large, this tells us that the amount of product compared to the amount of reactant is a lot larger. So the forward reaction in this case, going this way, is favored. So the way we actually show that, here's a little picture representation. If we have a lot more products, that means our K equilibrium constant is a lot larger than 1, and the reaction is product favored, and product predominates at equilibrium. If, for example, we have a large amount of reactants compared to products, this tells us that at equilibrium our K constant is a lot smaller than 1. The reaction is then called reactant favored, and reactant predominates at equilibrium. Also, something else to note is the equilibrium constant of a reaction in the reverse is the reciprocal of the equilibrium constant of the forward reaction. So, for example, if we go back to the same reaction that we were talking about in the previous board, we have NO2 making N2O4. If, let's say, for the forward reaction, equilibrium would be 10, for the reverse reaction, equilibrium would be 1 over 10. So the K equilibrium of the reverse reaction is the reciprocal of the forward reaction. Okay, so I'm going to move over this board. Okay, let's look at a couple of examples of manipulating K equilibrium. And for instance, let's say that we have a stepwise reaction. This would be step 2. So in step 1, let's say that we have A plus B makes AB. Its equilibrium, I'm going to call it K equilibrium 1, is, let's say, arbitrary number is 100. For step 2, if we're now adding the intermediate AB and we're adding some C, we form D. Its equilibrium constant would be 10. The overall reaction, which we see that AB cancels out, AB is an intermediate. To get the K equilibrium for the overall reaction, we multiply the two equilibriums for the stepwise reaction. So this is for step 1, and step 2, we multiply 100 by 10 to give us a new K equilibrium for the overall reaction. Another important point is that if we're talking about concentrations of solids and liquids, those two are essentially constant throughout the reaction at a given temperature. Equilibrium is very sensitive to temperature, so your K equilibrium value will change with different temperatures. But however, if we're talking about solids and liquids, those essentially do not change. So they play no part in the equilibrium expression. So for example, if we're talking about the dissociation of lead chloride to give us lead 2+ ions and 2 chloride ions, the way we would draw its equilibrium expression is we have the product of the two concentrations of the ions, but however, we do not put the solid in the denominator because PbCl2 is a solid, and we know that because we have our little subscript S, which tells us that this is a solid. This plays no part in the equilibrium expression, therefore K equilibrium is just the product of the two ions. And that's it for today.